Welcome to this lecture. This is the final lecture of week 8 and this is also the final lecture of this course. In this lecture, we are going to discuss some problems and exercises based on the content of this week. Remember that in this week, we have looked at some further properties of weak convergence. In particular, we have looked at certain extensions of the Lindeberg-Levy central limit theorem through the Lindeberg's and Lyapunov's conditions, which allows us to look at some collections of independent random variables, but with not necessarily identical distributions satisfying certain central limit theorem, and that is what is given in terms of the Lindeberg's and Lyapunov's conditions. We have also looked at some other approximation statements in terms of the Slutsky's theorem and the delta method. We have also seen extensions of central limit theorem in the higher dimensional setting. So, in this lecture what we do is that we look at some applications of the results that we have discussed in this week. Let us discuss through the lecture notes. Alright. So, let us look at some problems and examples based on this content of this week. Alright. So, we start with some nice applications of the Slutsky's theorem, which was discussed in theorem 4 of this week. So, we start by looking at a sequence x n of IID random variables, and here we will assume that these random variables that we are considering are non-degenerate, and that is essentially given by the assumption that the variance of x 1 is positive. Now, remember we have discussed this earlier in remark 5 of week 5, that as a consequence of properties of convergence in probability and through the law of large numbers, we can show that the sample standard deviation converges in probability to the population standard deviation as n goes to infinity. So, here what is the sample standard deviation? It is given by this expression of the sample variances, that we look at all the these terms from the sample mean, the square of that we add them up, but scale by n minus 1. So, the justification of that was also given, that corresponding choice of 1 by n minus 1 helps in looking at the fact that expected value of S n squared will be the correct thing that we want. So, that is why this choice of 1 by n minus 1 comes in. Now, here as always x n bar denotes the sample mean. Now, here you note that this convergence that we had discussed earlier, in turn we can write is using this form, that again in the sense of convergence in probability, square root variance of x 1 divided by S n converges to the degenerate random variable 1 as n goes to infinity. We are going to use this result in our subsequent computation. So, let us just mark this. So, we now go back to the Lindeberg-Levy central limit theorem, which we have discussed earlier. So, this tells you that square root n divided by sigma multiplied by this centering of the sample mean converges to a standard normal random variable z in the sense of weak convergence as n goes to infinity. Now, here given this weak convergence and this convergence in probability that was mentioned in star, we are going to appeal to the Slutsky's theorem and say that the product of these quantities will also converge in the sense of weak convergence to the product of the limits. Now, the product of the limits is just z, but then this product as you see here, that actually can be simplified and written by this expression, that what we are doing is that given this sample values x 1, x 2, x n, which are certain now random samples, you compute the sample mean and you also compute the sample standard deviation. Then you also know the number of samples. So, that actually gives you certain kind of procedure for estimating expected value of x 1. So, this is the application of this result, that in the sense of weak convergence, this is essentially giving you some estimate for expected value of x 1 if that is unknown. Alright. So, this is a nice application of the Slutsky's theorem together with our earlier results on convergence in probability following from the law of large numbers, and finally, we have applied to the Slutsky's theorem. Alright. So, now we move on and look at some other properties of weak convergence. Recall that in the previous weeks, we have looked at very nice properties of weak convergence. In particular, we have mentioned that the continuous mapping theorem holds for the weak convergence, meaning if a sequence of random variables x n's converge to x in the sense of weak convergence, then by applying a continuous function, we will get a new sequence. Let us say f is a continuous function, then I will get the sequence f of x n, and as n goes to infinity, this will converge to f of x in the sense of weak convergence. So, this is the statement of the continuous mapping theorem. In particular, we have discussed this earlier, that by just looking at a affine transformation, meaning map small x to a x plus b, where a and b are some fixed real numbers, then this is a nice continuous function which is in some affine form, and therefore, as a consequence of the weak convergence property of the continuous mapping theorem, what we get is that if x n's converge to x in the sense of weak convergence, then a x n plus b converge to a x plus b. So, this result we had discussed earlier in note 7 of week 6. So, this is exactly the result that we recalled. Now, we can generalize this approximation result further by taking sequences of real numbers which converge to a and b respectively. So, what happens is that we now can look at this new sequence of random variables. So, earlier we had looked at a x n plus b, but now I am saying that we are going to vary a's and b's through n. So, here what is happening is that a and b, these numbers in n, we can treat them as degenerate random variables. So, in particular, by appealing to the Slutsky's theorem, first we will say that a n times x n converge in the sense of weak convergence to a times x. So, here we are appealing to the fact that a n's, the degenerate random variables, converge in probability to the degenerate random variable a, and it is given that x n's converge to x in the sense of weak convergence. So, that is the application of the Slutsky's theorem. But again, we now look at this new sequence of random variables b n, which are again degenerate, and they converge in probability to the degenerate random variable b, and therefore, just by addition property of the Slutsky's theorem, we will immediately end up having that a n x n plus b n converge weakly to a x plus b. So, this is a nice application of Slutsky's theorem that allows us to extend the previous result. We now look at some further nice properties of weak convergence. So, here we first recall some important structural properties of weak convergence. Remember, when we discuss weak convergence of random vectors, what we have said is that all linear combinations of the component random variables must converge to the appropriate linear combination of the limit random vectors components. So, that is exactly the Cramer-Wald device that we have studied earlier. So, in particular, if you have random vectors x n's converging to a random vector x in the sense of weak convergence, you will have that the component random variables themselves will converge to the component random variables. For example, if you look at the first component, let us call it as x n 1, then it must converge to the first component of the limit random vector. So, that idea is very simple, you just have to look at the linear combinations given by 1 and followed by 0. So, if you choose these coefficients for the linear combinations, you just extract the first component random variable out of the random vector, and that is how you will get that if you have that the random vector converges in the sense of weak convergence, you will have the convergence of the component wise random variables, and this convergence is in the sense of weak convergence. But now we can ask the opposite question, what if I want to go from the component wise convergence of the random vector to the weak convergence of the original random vector. So, we are going to discuss some special case under which we can discuss that result. So, let us see. So, what we start off with is that suppose we are given that we have this 2 dimensional random vector converging to this random vector, and by the Cramer-Wald device we will immediately have that if you choose any vector u in R2, the u transpose of this sequence of random vectors will converge in the sense of weak convergence to this thing. So, that is essentially giving you all these linear combinations of the component random variables. But now, let us choose the specific vector u with components 1 and -1. What happens is that then u transpose x n y n simplifies and gives you just x n minus y n. On the other hand, the limit random vector, if you act it with this u in the sense of this u transpose action, then you will just end up with x minus y, and as a consequence what we are saying is that x n minus y n, that linear combination converges to x minus y. So, this is a nice property of the convergence of the random vectors, that you get these corresponding convergences in terms of the combinations of the component random variables. You can also try to choose the vector, let us call it u again, with components 1 1. Then what happens? Check it that which linear combination converges to the appropriate linear combination in the limit. So, again here is where what was being suggested earlier, that you have to choose this kind of vectors, let us say, that will give you the fact that corresponding components will converge. So, that is the component wise convergence that you get for free if the original random vectors converge. So, these are some nice applications of the Cramer-Wald device that tells you that if you have the convergence of random vectors, then the corresponding component wise random variables converge, and also their linear combinations also converges. But now, we want to talk about the converged direction. So, let us observe this, that suppose now for each natural number n, look at these random variables and assume that for each number n, x n and y n are independent. So, at each level the 2 random variables that we are considering are independent. Then what happens is that if you look at the characteristic function of the random vector with components x n and y n, then for all u v in the real line, if you evaluate it, that will just factor out. This is simply using the independence of the component random variables x n and y n. So, here note that we have not assumed any kind of independence involving all x n's and all y n's. What we are saying is that individually x n and y n, meaning at each level, they are independent, and this is the application of independence that we are appealing to here. Now, suppose that the sequence of random variables x n that we have considered, it converges in the sense of weak convergence to a random variable x, and similarly the other sequence of random variables y n converge in the sense of weak convergence to a random variable y. In addition, assume that we can choose these random variables x and y to be independent. So, here note that first you can construct the limits, let us call them x tilde and y tilde if they have it. So, suppose you have that, then if required you can always go to a different probability space in the sense of the product measure structures that we have discussed earlier in week 2, and you can construct the copies of x tilde and y tilde on that new probability space with independence property. So, this property of independence that we are asking is not a strong condition, and in the sense of weak convergence we do not require any way that the random variables are defined on the same probability space. So, you can always go to a different probability space and construct random variables x and y with the same distributions as x tilde and y tilde respectively, and moreover x and y should be independent. So, that kind of constructions we have discussed earlier in week 2 as well as in part of the discussion involving the characteristic functions. So, please go back and check. But now, suppose you assume that these x and y are independent, then what happens? Then let us look at the pointwise convergence of this characteristic function of this random vector in question. What happens is that as n goes to infinity, this characteristic function first of all splits out. So, therefore, we can simply look at the product of the individual limits here. But now, if x n's converge to x and y n's converge to y in the sense of weak convergence, then by the Levy's continuity theorem, the corresponding characteristic functions pointwise will converge to the product of the characteristic functions of x and y evaluated at the points u and v respectively. But now, if x and y are independent, then again using the property of independence, we will say that we can actually now look at the characteristic function of the random vector with the component random variables given by x and y evaluated at the point u v. But now, this calculation that we have just done here, u and v are actually arbitrary, but fixed. But since this is true for all such choices of u and v, we can now go and discuss about the Levy's continuity theorem in the higher dimensional setting, and therefore, by the pointwise convergence of the corresponding characteristic functions for the random vectors, we will conclude that the corresponding random vectors converge in the sense of weak convergence to the appropriate limit random vector. So, here what is happening is that we have justified the convergence of the random vector starting with the component wise convergences, but in addition we have assumed that x n's and y n's are independent and x and y are independent. Under that assumption, we have lifted the convergence of the random variables to the corresponding convergence of the random vector. So, here what we are actually using in the background are the structures of the joint probability distribution. So, here joint law of the random vector actually splits out and becomes this product of the marginal laws. So, this we have discussed earlier, that as long as you are talking about independent random variables, then the distribution of the random vector essentially splits out in terms of the marginal distributions. So, that is the property of independence that we have already seen earlier. But now, this description of weak convergence of random variables that we have just seen can again be stated in terms of the corresponding laws. So, what we will get is this statement, that suppose you consider weak convergence of Borel probability measures on R 2, but suppose these Borel probability measures are actually coming as product measures with these components, that suppose mu, mu 1, mu 2 and so on, and nu, nu 1, nu 2 so on are Borel probability measures on one dimension. Construct Borel probability measures on R 2 as product measures of these. Then the statement says that this will converge to the product measure of mu with nu if and only if mu n's converge to mu and nu n's converge to nu. So, this is essentially a restatement of whatever we have just discussed. So, please try to restate the calculations that we have just mentioned in terms of the underlying joint probability distribution, and you will immediately get this fact that we have just stated. Please take this as an exercise. All right. But now, here we want to make some further interesting comments. So, here we recall some setup from the Slutsky's theorem. So, here we first fix a constant c in the real line. If it so happens that a sequence of random variables x n converge weakly to x and y n's converge weakly to the constant c. In fact, this also will become convergence in probability that we have seen earlier. The Slutsky's theorem can also be stated in the form of convergence of random vectors in this setting, that the random vector x n y n with these components converges weakly to the random vector involving the components x and c. So, this is just another way of stating the Slutsky's theorem, and in particular if you appeal to this Cramer-Wald device, then you just appeal to these projections along some arbitrary vectors u, and in particular by choosing those vectors u appropriately, you can now look at the addition, subtraction and all those business in terms of the component random variables, and they will now converge to the correct limit in the sense of weak convergence. Here what is happening is that in the limit random vector, the components are x and this degenerate random variable c. You can check that x and c are actually independent, but here in the setting of Slutsky's theorem, we did not require that at the level of approximations these x n's and y n's are independent. We did not assume that in the Slutsky's theorem. So, this is just a comparable result where the second sequence is converging to a degenerate random variable. So, therefore, what we are saying is that in general you have to assume the appropriate convergences, and if you have the independence of the components as well as the limits, then you can lift it up from one dimensional weak convergence to higher dimensional setting. But here in the Slutsky's theorem setting, what we are essentially saying is that if the limit random variable for one sequence is a degenerate random variable, you do not really require that, and that is what is getting used in the Slutsky's theorem setting. All right. So, we now discuss another interesting example of the classical central limit theorem and further application of the delta method. What we do is that we look at a sequence of IID random variables, and for simplicity we will go with normal 0 1 random variables. Now, here note that the square of any normal 0 1 random variable is actually following a chi-square distribution with 1 degrees of freedom, what we typically say as chi-squared 1. So, if you now look at these new random variables as x n squared, they are now independent and identically distributed random variables with the common distribution given as chi-squared 1. So, let us now look at the mean and variance of these new random variables. So, here the common mean is given as expected x 1 squared, that is nothing but the variance of x 1, because remember expected value of x 1 is 0. So, that is what we use here, and therefore, variance of x 1 is exactly equal to the second moment here, which is 1. So, that is fine, but let us now try to compute the variance of x 1 squared. So, how do you compute this? So, here again we go back to the similar expansion. So, you have to look at the second moment of x 1 squared, which is the fourth moment of x 1 minus the square of the corresponding mean. We have already computed this quantity. Now, we have to look at the fourth moment of the standard normal random variable, which actually turns out to be 3. So, we are just computing 3 minus 1 here, which turns out to be 2. So, we have now computed the common mean and variance of this sequence of IID random variables x n squared. So, we can apply the Lindeberg-Levy central limit theorem for this new sequence. All right. So, let us see what happens. So, we have to subtract out the mean and scale it accordingly. So, therefore, the sum of the random variables, the centered and scaled versions as per the classical central limit theorem or the Lindeberg-Levy central limit theorem converges in the sense of weak convergence to a normal random variable with mean 0, variance 1. Now, we can rewrite in terms of the sample mean description. So, let us see. So, we just have to scale it accordingly, and then what we get is that we get this square root n scaling for the convergence of the corresponding sample mean setting. So, we subtract out the mean of the original distribution, and we will get that we just have to scale it accordingly. So, this is just a standard manipulation that we do. Here the limit random variable turns out to follow the normal distribution with mean 0 and variance 2. So, this is a very simple calculation, just simplify this previous expression in terms of the sample mean description as we are writing here. So, please verify this if you are not comfortable with these calculations. Now, let us apply a new function on top of it, which is this function, and this is where we are going to apply the delta method. What we do is that we look at this function, which for positive x gives you square root of x, 0 otherwise. So, this is a nice continuous function. Moreover, this is also differentiable at the mean that we want. So, therefore, we compute the corresponding derivative of g at the point, and here if we appeal to the delta method, then we will immediately have, by applying the square root function, we will get the corresponding convergence with the same scaling square root n to this quantity. So, here we are simply writing g prime of the number times the original limit random variable. So, that is exactly this we are simplifying. So, this is following normal distribution with mean 0 variance half, all right. So, if you were to multiply both sides by square root 2, so we can essentially get rid of the half variance on the limit, and we can state it in terms of the normal 0 1 random variables. So, the original statement that we have derived, we just rewrite using this setting, that square root 2 multiplying this quantity converges in distribution to a standard normal random variable as n goes to infinity, all right. So, this here gives you some nice application of the Lindenberg-Levy central limit theorem together with the delta method, and the delta method essentially allows you to preserve the same rate of convergence, but here we require that the function that we are using has appropriate differentiability properties. So, in this lecture we have seen some further nice examples and properties involving weak convergence of random variables and random vectors. Hopefully, these results will help you understand the content of this week better. We stop here. This is also the final lecture of this course. I hope that the discussion that we performed will be helpful for your future studies. We stop here. Thank you.